Perfect. Thanks, Ivan. So yesterday we took quite some time to define what initial data sets are and analyze their properties, and understanding in particular what extrinsic curvature is. So this part of the plan we've achieved. So for today, we are left with understanding asymptotic flatness and then recalling the most common notions of energy, linear momentum, and mass of asymptotically flat initial data sets. And then by the end, culminate in understanding better what's the center of mass and why is it difficult and where is it, if it's anywhere. So that's the plan for today. And so for the chapter of asymptotic flatness and all the remaining chapters of this lecture, I'll always consider an initial data set M, G, K, mu, J, which is always assumed, and I won't write this every time, otherwise I'll be too busy, is always going to be assumed to satisfy these Einstein constraint equations that I showed you at the end of yesterday. So whenever I say initial data set now, it's presumed that the initial data set satisfies these constraints. And also from now on, I'm going to set G to 1 and C to 1 by picking units accordingly, because it's going to be too long to print them every time or write them every time. And so with this prelude, I can now say what I mean by an asymptotically Euclidean or asymptotically flat initial data set. And let me first draw a picture. So if this is my manifold M, now this is a two-dimensional sketch of a three-dimensional manifold, and this is my Euclidean space R3, then what I want asymptotically Euclidean or asymptotically flat to mean is that far out, say outside some compact set here, well, this is compact and I'm excising it. So far outside this compact set, in the region near what I want to define as infinity, I have a diffeomorphism, which can either be called phi, or we will see it will be called X later, into R3, but only mapping to the exterior of a ball. So this is a closed ball in R3, so that every point in this exterior region in the manifold outside the compact set, so this one is going to be called the exterior region, maps onto precisely one point of the exterior of this ball in R3, and injectively so it's this is a diffeomorphism. We don't know what the term diffeomorphism means. It means it's a one-to-one onto map between this exterior region M3 outside the compact set. In orange in the picture, onto this exterior region of the ball in Euclidean space. So this is bijective, one-to-one and onto, and it's smooth in both directions. So it's smooth and its inverse is smooth. Okay. So I have such a diffeomorphism, which means that in some sense, if you want, I can identify points on this manifold, on this exterior region of the manifold, with points in the exterior region of the ball in R3, and just pretend that all the interesting topology of the manifold is hidden inside this compact set. And now I'm just talking about points in the exterior of the ball, of some ball in R3. And using this diffeomorphism, another way of saying this is that any point P here in this exterior region of the manifold uniquely correspond to a point X in R3. And then I can identify the numbers X1, X2, and X3 and this vector X as the coordinates of this point P, or I can identify the point P even with this vector X in R3. And if I do that, if I have a scenario where I have such coordinates or such a diffeomorphism, those are two different ways of saying that very same thing, then I can say things about the metric G, and the second fundamental form K, and the mass metric, the energy density mu, and the momentum density J decaying as the radius goes to infinity, where here the radial variable r is going to be the usual Euclidean radius. Okay, so with respect to these coordinates, xi or x on M3 outside my compact set, then I want that the components of the metric in these coordinates look like delta ij plus terms of the order r minus eta, r to the power minus eta. I'll explain in a second. Terms of the order, the k components should look like terms of the order r to the minus eta minus 1, and mu and ji should be integrable. And now I'm going to add a little 2 here and a little 1 here, and I'm going to say in a moment what all this means. And this is as the radius goes to infinity, where we call the radius was the length of this coordinate vector x. And then I say this is asymptotically Euclidean. Oops. Euclidean or asymptotically flat, and abbreviated this is either AE or AF for asymptotically Euclidean or asymptotically flat of decay rate eta bigger than 1, bigger than 0, sorry. Okay, so if I have these coordinates, and with respect to these coordinates, the components of the metric and the second fundamental form decay as it's written there, and the matter density, the energy density, and the component of the momentum densities. This is integrability. It's integrable in L1. As you know it, for example, from quantum mechanics, there you usually want L2, here we want L1. Then we call this asymptotically Euclidean. And now what are these terms? These O notation terms here, and these little indices in particular. So I presume that most of you are familiar with the capital O notation. So if some function or some component of some tensor is in O of r to the minus eta, that means that it decays at least as fast as r to the minus eta. And now if I have a little index, that means that at least the number of derivatives corresponding to the index decay correspondingly. So if my function decays like r to the minus eta, then its derivative is supposed to decay like r to the minus eta minus 1, and its second derivative should decay like at least as fast as r to the minus eta minus 2, and so on and so forth. Okay, so if I pretend, then this is a statement also about decay of up to 2 derivatives in Gij and up to 1 derivative in Kij. Okay, so let me say this again. I say that my initial data set is asymptotically Euclidean if there is a compact set such that outside this compact set I have these coordinates in which the components of the metric and the second fundamental form decay as it's written here as I'm going out to infinity, and the meta quantities are integrable. Okay, and then I say it's integrable, it's asymptotically Euclidean of decay rate eta if this holds. And it could of course be also asymptotically Euclidean of a different decay rate, if like a smaller one. Okay, so this is the definition, and we will see later why this integrability condition is there, and also a little bit what this decay rate eta really means here. There's of course also a definition of asymptotic flatness for spacetimes, not just for initial data sets, that you can define via Penrose diagrams. And I want to say that this one is nicely consistent. So if you have a spacetime which is asymptotic to Minkowski via a Penrose diagram approach, for example, and you have an initial data set in that spacetime which reaches space like infinity in your Penrose diagram, then it will satisfy conditions of this form in suitable coordinates. And on the other hand, if you consider other time slices in a asymptotically Minkowskian spacetime, they don't necessarily have to be asymptotically Euclidean. And I want to just, as a warning, give you an example. So if you are in Minkowski, this is exact Minkowski, and I'm only drawing a TR diagram here because everything can be done stereosymmetrically, then I can have an initial data set, which is a hyperboloid, rotational hyperboloid, sitting tangentially, asymptotically tangentially in the light cone, other than my sketch implies, and that one will not be asymptotically Euclidean. So this is a perfectly fine hyperboloidal, as we call it, initial data set. It's not asymptotically Euclidean. So not all initial data sets, even if they in some sense go far out, are asymptotically Euclidean, not even in Minkowski. So this is just a warning, and maybe a much better news is that if you have an asymptotically Euclidean initial data set, and if you evolve it into a spacetime, as we very briefly discussed yesterday, by using lapse and shift approach, and if that lapse and shift decay suitably fast, consistently with the decay conditions I wrote down here for the initial data set, then the spacetime will generate, is generated will also be asymptotic to Minkowski. So if an initial data set is asymptotically Euclidean and lapse, shift, decay, and I won't go into this, so I'll just say accordingly, then the generated spacetime, and by generated, I mean via the Einstein equations for some meta model where we know how this works, it will be asymptotic to flat. The reason why I prefer to call it asymptotically Euclidean over asymptotically flat is then, first of all, it's more clear that we're in the Riemannian case where the model is Euclidean and not Minkowski. Otherwise, it's a little bit ambiguous. And also the term here in the asymptotic is the Euclidean metric in Cartesian coordinates, the Kronecker delta, and not the Euclidean metric in some other coordinates like spherical polars, which asymptotically flat as a term somehow suggests should also be allowed. So that's why I personally prefer asymptotically Euclidean. In the literature, you'll find both used synonymously typically. Okay, so here's an example. We look at the spatial Schwarzschild. Recall this was the canonical initial data set in the Schwarzschild spacetime. And there we had that G is 1 over n squared dr squared plus r squared d omega squared, k 0, mu 0, and j is 0. So if we now want to verify these asymptotic flatness conditions, we need to find coordinates first, in which we say that it's asymptotically Euclidean. Regardless of which coordinates we pick, these are always 0, so they always satisfy this integrability condition no matter what coordinate chart I'm picking. So integrability is okay. And also, regardless of which coordinate chart I will be picking, k will decay to 0 suitably fast because it's identically 0. So this is also going to be okay. So I only need to worry about the metric components here. And because I just said that what I need is that the metric components asymptote to the Euclidean metric in Cartesian coordinates. So to the Kronecker delta ij, and I have this on one page, no, so I'll copy it here. So this is what I want to achieve. Hello. And maybe I should write that n was 1 minus 2n over r, take the square root. Now I need to switch into some Cartesian coordinates related to these spherical polar coordinates in the Schwarzschild metric. Okay, so I will do that by saying that x1 should be r cosine theta, cosine phi, and so on, just like I would transform from polar coordinates, spherical polar coordinates into Cartesian coordinates in Euclidean space. Yeah, transform to Euclidean, to Cartesian coordinates from polars. And then I will need to write the Schwarzschild metric here in these new coordinates. So how do I do this? Well, I write G is 1 on n squared dr squared plus r squared d omega squared. So then Gij in my new coordinates x will be 1 on n squared dr dxi dr dxj plus r squared. Oh, now I'm using a trick. Let me first explain the trick. So I'm writing r squared d omega squared as the Euclidean metric minus the r squared. This is the Euclidean metric in spherical polars. So I don't have to use angular variables and their partial derivatives. This is a neat trick that I recommend to remember if you ever have to work with things like this. So then instead of adding r squared d omega squared, I will now just write delta ij minus dr dxi dr dxj. Okay. Any questions?
Yeah, we had one. Sapir Jafari asks, could you repeat why you prefer asymptotically Euclidean over asymptotically flat?
Yes, I will in just a second. Someone's just opening my office door. I'll just lock my door and then I'll.
Okay.
It appears a sign is not enough. Okay, so why I prefer the term asymptotically Euclidean over the term asymptotically flat is that there's two reasons. One is that we also use the term asymptotically flat to refer to spacetimes that are asymptotic to Minkowski spacetime. And I don't want to get people confused. This is only about initial data sets, not about spacetimes. And the second reason, and maybe more important reason, is that in this asymptotic decay that I'm imposing here, I want this delta ij really to be the Kronecker delta. So the components of the Euclidean metric with respect to some Cartesian coordinate system, some rectilinear coordinate system, and not the Euclidean metric in spherical polars or other coordinates. And that's why I'm referring to Euclidean rather than flat, because flat would suggest I would have more flexibility there. But I mean, the definition is what's circled there. And as long as you use the correct definition, you should feel free to call it whatever you find suitable. Okay, so now we've computed here the components of the Schwarzschild metric in these new Cartesian coordinates that we've constructed from the spherical polar coordinates as we would in Euclidean space. And now we need to make some asymptotic analysis to see if they satisfy this decay assumption for which rates beta, right? So I'll regroup this. We already have a nice delta ij, and then we have 1 on n squared minus 1 dr dxi dr dxj, and then I can compute that this is nothing else but xi xj over r squared, because this is just the usual transformation between spherical polars and Cartesians. And this, by the definition of the lapse in Schwarzschild, is 1 minus 2m over r minus 1. And this I can expand into a power series, and then I will get 2m over r plus terms of the order 1 on r squared. So if I summarize this, I will get delta ij plus 2m over r xi xj over r squared plus terms of the order 1 on r squared, where I'm using that this is bounded and all derivative of it decay accordingly. So I can swallow this into this. Okay. And in other words, I can certainly write this as delta ij plus O2 of 1 on r. So it's asymptotically Euclidean of rate theta equals 1 or any smaller rate. So this was a hopefully rather straightforward example. Is that roughly clear? Okay. So then I'll go back to this graphical stuff that I explained yesterday, just to give you a feeling for how these computations work and show you under which assumptions on the graph function they will be asymptotically Euclidean and under which rate. So example 2, we will look at the graphical initial data sets in Schwarzschild. And they will also become important later for understanding why the center of mass is so complicated to define. And I will assume that the graph function t is of order r to the alpha, with including 3 derivatives. Okay. And so I'm recalling that the components of the induced metric on the graphical hypersurface can be computed as gij minus n squared di dj. So now if I'm using my decay, then gi is like r to the alpha minus 1, and same for tj. The lapse is asymptotic to 1, and the Schwarzschild part, this part here, I just showed that it's asymptotically Euclidean of rate 1. So I can rewrite this as delta ij plus O2 r to the minus 1. That's the Schwarzschild part, minus order 2 r to the 2 alpha minus at least 2. Okay. And I'll comment on this in a second, but let's keep it like this. And let's maybe only point out that I started here with a 3 in order to get a 2 here, which I needed for the definition of asymptotic Euclideanness. And for the components of the second fundamental form, this was a little bit more lengthy. So I had di and j plus tj and I plus n the g dash of t minus n squared di j n squared gt divided by the square root. This was the second fundamental form I told you one can compute yesterday, and we examined this formula a little bit yesterday. So let's go through this term by term. Ti we know is like 2 r to the alpha minus 1. The same is true for tj, and the same is true for those here, and also for the t that gets one derivative here. Then what about the nj? So, well, we know that n is the square root of 1 to m over r. So this is the same as 1 minus m over r plus order 1 on r squared. So then nj is like m over r squared, r cubed xj plus lower order terms. Yeah, this is just power series analysis for nice smooth functions. And so in particular, this is just O infinity of 1 on r squared. So then that means that this term here and this term here, they're actually this good. And n we already analyzed, and so the term I still need to analyze is this Hessian and also this grad g here. And so what and also of course the denominator, but the denominator is very similar to what I did in the metric already. So what I find is that this is terms of the order O2 r to the alpha minus 3 from the first two, then a term of order 1 r to the alpha minus 2 from the second partial derivatives of t. That's why there's a little 1 in the index also. And then from this term here, from the red term, I also get a Christoffel symbol term. And there I would need to use what I first showed you up here for the Schwarzschild metric in these coordinates. And I'm not going to show you all the details, but what you get from an analysis of those Christoffel symbols is r alpha minus 3. And then from this last term, this mixed term, which has n derivatives and t derivatives, I get some r3 alpha minus 5. And the denominator is 1 plus O2 right to the 2 alpha minus 2. Okay, so I'm cutting it a little bit short, but I want to show you a little bit the style of this. And of course, we found yesterday that ut and jt are 0, so integrability is a no-brainer again. So we've checked the metric. The metric has whatever is the worst decay of these two. So for example, for non-positive alpha, this would be okay. Then this would be decaying. And here, if alpha is non-positive, then this is certainly decaying, this is certainly decaying, this is certainly decaying, and this is certainly decaying if alpha is small enough. I mean, if alpha is non-positive, then all of them are decaying, and even some positive alpha would be allowed. So then we conclude that alpha less than or equal to 0 will do, and beta depends on alpha. So this is just to show you a little bit how such computations will work and why we can expect graphs with decaying graph function. That's what we assume, that if alpha is non-positive, then this graph function is either just bounded or even decaying. Then the induced initial data set information on this graphical hypersurface will be asymptotically Euclidean of some rate eta, which depends on this alpha. Okay, one last comment I want to make about these asymptotic Euclideanness assumptions is that they are Poincare covariant. Conditions are Poincare covariant. I already said that if you start with asymptotically Euclidean initial data and you evolve them in time with lapse and shift decaying suitably fast to the Euclidean, to the Minkowski versions of them, then the spacetime that generates is asymptotically Euclidean, asymptotically Minkowskian. And but the same is actually true for infinitesimal boosts. So if you start boosting your slice a little bit in a given asymptotically Minkowskian spacetime, so that lapse and shift are asymptotic to those of a boost in Minkowski spacetime, then these asymptotically Euclidean conditions are going to be preserved. If you have an asymptotically Minkowskian spacetime and you start with some asymptotically Euclidean initial data set and you evolve it in time with lapse and shift decaying to those of time translation in Minkowski spacetime, then they are preserved. And also, if you translate or rotate coordinates on your initial data set, so if you do some Euclidean motion on your coordinates, then also these conditions are preserved. So they're Poincare covariant or invariant. Maybe.
So Carla, that would be
Yes.
that would be like in boosts, like in special relativity, like the same boost everywhere, right?
Yes,
Like,
the same, like some asymptotic to a boost, right? To a special
okay.
relativity. Yeah. Other questions?
No, we don't have anything else at the moment, I don't think.
Okay, so then let's keep this more mathy stuff at the back of our minds and move on to the more physicsy stuff of energy, linear momentum, and mass. And here, I'll admit right away, I'm not going to go into any degree of detail. I'm just going to try to explain to you what is important to later understand the problem of the centered mass and some of the math that sits behind it that is important in view of later. And I'm going to skip everything that's not important in view of later for the sake of time and also because I'm not a particular expert on it. So what do we mean here by energy, linear momentum, and mass? Again, we're going to consider a given initial data set, which is now assumed to be asymptotically Euclidean of some rate eta beta than 0. And of course, this presumes that the constrained equations are satisfied. And now what I want to define is I want to define the asymptotic energy, so total energy of this whole initial data set, and the total linear momentum of this whole initial data set, and the total mass of this whole initial data set, in a way that in some vague sense, they correspond to energy, linear momentum, and mass as we understand it from special relativity. So that we have some energy momentum flow vector, and the length of it is the mass, and it transforms covariantly under the Poincare group. And interpreting this, in some sense, I want to say that I'm looking at this relativistic system modeled by this initial data set at a given instant of time, asymptotically Euclidean means it's suitably isolated from external influences. So it's really an isolated relativistic system at a given instant of time, observed by some observer. And then I want to compute its total energy, total linear momentum, and total mass as seen by this observer. And then Poincare covariance just means that if I had picked a different observer, so a different initial data set in the same space-time, then I would have my energy momentum four vector transform as it would in special relativity under a change of observers. Okay, I can't make this precise now, unfortunately, but I hope that the idea comes across what I want. Okay, and so these notions were defined by Arnold, Gieser, and Misner in the 60s. I forget the exact year, unfortunately, and they call the ADM quantities for that reason: Arnold, Gieser, and Misner, ADM energy, ADM linear momentum, and ADM mass. They also defined an angular momentum, but I'm not going to go into that today. Okay, so those are the quantities, and they're all defined implicitly, typically, with respect to such a given asymptotic Euclidean chart, a given coordinate chart x as above. So when I say AE, I mean asymptotically Euclidean with respect to a fixed specific chart. It's generic, it doesn't matter which chart you take, but it has to be fixed. And a priori, all these quantities could depend on this chart. And we will discuss this a little bit later. And then here are the formulas. The ADM energy is defined as 1/16 pi. The limit as the radius goes to infinity of the integral over the sphere of radius r around the origin over the sum 1 to 3 for the coordinates ij of the components partial ij, take a j derivative minus partial jj dxi, and then xi over r dA delta x. Okay, dA delta is the area element induced on the sphere of radius r around the origin in Euclidean space. That's what the delta means. This here is just the Euclidean normal to the sphere, the ith component of the Euclidean normal, and the sum is the sum over these coordinates. So it's a surface integral at infinity over partial derivatives of the components of the metric in this given coordinate chart. And a priori, there's no reason why it should be the same answer for each coordinate chart, except that, of course, they didn't just guess this expression, but they derived it from a Hamiltonian analysis perspective, from which you would hope that you would get the same result for every such chart, and you do, under some constraints that I'll mention later. Okay, so this is the formula they derived through a Hamiltonian systems analysis on infinite dimensional spaces. So this is a complicated thing that they did. And they also derived the formula for the linear momentum. And I write down the jth component, and then it's 1/8 pi, the limit as r goes to infinity, the integral of s to r0, sum of I from 1 to 3, and then components of the second fundamental form tensor k, kij minus trace gk, gij, xi over r, dA delta of x. So it's a very similar expression in style. It's also a surface integral at infinity, where we integrate with respect to the Euclidean area measure, or just as you would as a physicist. If I didn't ask you how you would do this integral, you would just do it this way probably. And note that the expression here is very similar to the constraint, to the momentum constraint expression. And then I'll get back to that in a second. And again, this is also derived by a Hamiltonian systems analysis by Arnold, Gieser, and Misner. And then this ADM mass is defined as the square root of P ADM squared minus the Euclidean length of this vector P ADM squared. And another way to express this is as the square root of the absolute value of the Minkowskian length of this energy momentum vector. Oops. Okay, so this is the Minkowskian length of this energy momentum vector, as you would expect from special relativity. Okay. So now for this to work, one needs the decay rate eta to be larger than 1/2. Okay? And I'll explain why. That's a bad color. Let's take this. Okay, let me explain why one needs this. The reason is an example found by Denisov and Soloviev already in the early 80s. Denisov and Soloviev. 80s. What they did is they looked at Euclidean manifold, Euclidean metric, K0, mu0, J0. So this is our canonical Minkowski initial data set, which is really just Euclidean 3 space. And this has coordinates x. And then they define new coordinates y as x plus a over square root of r x, where r again is the length of x and a is some real number. So this is a very valid coordinate transformation. It breaks down in the origin, but we only need coordinates outside some compact set. So we just excise some set around the origin, and then this is a perfectly nice coordinate transformation. And with respect to this coordinate transformation, then you can compute the components of this metric with respect to these new coordinates. And you will find that this is indeed asymptotically Euclidean of rate eta precisely 1/2. The 1/2 is due to the fact that we chose the square root here. Okay, that's where the 1/2 comes from. If you used a different power of r there, then you get a different power there. And so this fits into our framework because k is 0 and mu is 0 and j is 0. So this whole initial data set that they consider is asymptotically Euclidean of this rate 1/2. And if I compute the ADM energy of this metric with respect to these y coordinates, then I get an expression which is proportional to a, and in particular non-zero if a is non-zero. And if you've never seen this computation, maybe it's worthwhile to go back to this formula as an exercise, go back to this formula for the ADM energy, compute the components of the metric with respect to these funny coordinates. This is really just the Euclidean metric in funny coordinates, and then compute the energy of this metric in these coordinates and see how it relates to this parameter a in the story. So why is this telling us that at eta should be bigger than 1/2? Well, because this notion should measure the energy, and the energy of empty space, which Euclidean space should be empty space at initial time 0. The energy should vanish. So we expected that energy should be 0 for Euclidean space. Right? And it's non-zero in this example. In this example of an asymptotic coordinate chart on Euclidean space that we allowed before. That's why it's a good idea to exclude decay rates that are 1/2 or slower, and to assume that you have better decay than 1/2. And the way the mathematicians like to write this is instead of asking eta bigger than 1/2, one typically sees that eta should be 1/2 plus epsilon for epsilon positive. This seems like a little bit of overkill, but the reason why this is useful is because then the epsilon measures how much it's faster than 1/2, and that's really what one of the things one needs later. So if you open a paper, you will see this 1/2 plus epsilon there instead of the eta, usually. Okay, but now you hopefully understand why. Otherwise, the notion of energy doesn't seem to make sense.
We've got a
Questions?
couple of questions have come in, Carla. So first from Eric. So these both go back a little bit before the example. Eric says, I think you mentioned this, but how is that different how is it that different fixed coordinate charts lead to the same values of these terms?
We'll discuss that in a second.
Okay. And then the second question was from Gopal Yadav. How does the definition of ADM energy, how can the definition of the ADM energy formula be generalized to d-dimensional spacetimes? Is it that the limit R goes to infinity in integration over, I don't quite understand this. Is it, okay, I'll read out exactly what it says. Is it be like limit R goes to infinity in integration over remaining D plus one dimensional space-time? Maybe, I'm not sure exactly. Maybe the scaling.
No. So there is a very straightforward generalization of this formula to higher dimensions. Then let me pick some color. So this 1/16 pi will be replaced with some number that's related to the volume of the n-2. If the space is n-dimensional, then it will be related to the n-1 dimensional sphere. Then this here will be the n-1 dimensional sphere in that initial data set. And this will be the volume element, like your usual integration. And this formula won't change at all. Okay, so all you need to change are the things in yellow, and really the last expression you don't need to change either because it's natural. So instead of 16 pi, you will have some number related to the surface area of the n-1 dimensional sphere, and instead of the 2-dimensional sphere in the integration, you will have the n-1 dimensional sphere, and something similar for the ADM linear momentum. So they're very natural. The only thing you have to figure out is the normalization factor.
Okay, that's all we had, I think. Thank you.
Okay, good. So now I hope I convinced you that you want to have your decay rate always bigger than 1/2, or rather Denisov and Soloviev convinced you. And so now the next question is, why did I ask that mu and j are integrable? And I really asked this in coordinates. Why does this make sense? And this I want to justify by an analogy to Newtonian gravity. Where we really have a matter density, rho, and the mass is then defined as the volume integral over this matter density, as you usually do with matter densities. Then masses or mass densities, you integrate them, and this of course is finite if this matter density is integrable. So here we want an integrability of the matter density in order to have a well-defined mass. And so in analogy, it's not too surprising that in relativity, we want integrability of the energy and momentum densities in order to have well-defined energy and momentum. I hope this is convincing. Before I move on, let me make one more observation. In Newtonian gravity, we have this partial differential equation that the Newtonian potential is related to the matter density by Laplacian of u, and this is the Laplacian with respect to the Euclidean metric of u is 4 pi times the matter density, and u goes to 0 as r goes to infinity. So this is our Poisson system from Newtonian gravity. And using this, I can now go up here and continue here and plugging in this PDE, this partial differential equation, into my integral. Okay, this little delta always means that everything is with respect to the Euclidean space. So now let me copy this, so I have more room to write. So now I know that m is this in terms of the Newtonian potential, but this I can rewrite as 1/4 pi integral over I3, the divergence in Euclidean space of the gradient in Euclidean space of u. I only used some vector analysis there. And now I can use what is called the divergence theorem to rewrite this as a surface integral over surfaces at infinity. So I can write this as 1 over 4 pi, limit r to infinity is to r, or the origin of gradient u dot, let me just write it in grids, the normal vector into the area element. And then if you think about it, and I already mentioned it earlier, this is really nothing else than x over r in Euclidean space, the normal to the sphere. And so I can rewrite this as u du dxi dxi over r. And I forgot the sum. So the sum over 1 to 3 partial du dxi times dxi dr. And then I'm left with an expression that looks much, much more similar to the ADM quantities and helps getting a feeling for those. Okay, now if this expression is similar to the ADM quantities in style, yeah. Okay, so now we understood why the decay rate should always be bigger than 1/2. I hope I convinced you that it's a reasonable assumption that mu and j should be integrable, and also why it's not completely absurd to have quantities defined as surface integrals near infinity if they're supposed to measure total energy and total linear momentum and total mass. Questions? No.
We're good for now. We have one, but maybe we'll leave that one till the end because it's a bit off the main topic what you're talking about at the moment.
Okay, cool. Yeah. Thanks. Okay, so now that we looked at this in Euclidean space, let me state the theorem that somebody already implicitly asked about. So there's this theorem by Robert Bartnick from '86 who says that EADM is well defined and independent of coordinates if theta is bigger than 1/2. Okay, and the way he proves this is very similar to what I just showed you for the Newtonian case. So he rewrites EADM as a volume integral plus some inner boundary term via the divergent theorem. So he does it backwards. I did it forwards. I started with m being a volume integral over the matter density, and then I plugged in the Poisson equation to get it reworded into a surface integral at infinity. Now we're starting with a surface integral at infinity, which recall had this form that we have this xi over r here. So we have something multiplied by a normal integrated over a surface. And that's similar to here where we have something times a normal integrated over a surface. And so we do it backwards. Now we apply the divergence theorem backwards because we are on a manifold with inner boundary because we excise some compact set, we have some inner boundary term, but that doesn't bother me for the convergence of this integral at infinity. And I'm left with this volume integral, which is like some integral of the divergence of something. And this divergence of something, he relates to the energy density mu using the constraint equations, plus lower order terms. And then integrability of the mu tells you that this volume integral over the mu converges, and the lower order terms decay so fast that they also that their volume integral over them also converge, and the inner boundary term is at an inner boundary, so there's no worry about convergence. So this ensures this well-definedness, that the fact that this integral at infinity actually even converges. And this is how he uses integrability of the mu in this. So it's very similar to the Newtonian setting. I'm not sure if this is why he did this, maybe not, but this is how I understand why this is a great idea. And to show that it's independent of coordinates, what he does is he actually, and I lied to you a little bit there, he does this computation not in a generic asymptotic coordinate chart, but in one that's called harmonic. So the coordinates themselves satisfy the Laplace equation with respect to the Riemannian metric on the initial data set. And then he proves that such harmonic coordinates always exist and how they are related between different sets of asymptotic coordinates that are harmonic. He does this whole computation in one of these harmonic coordinate charts. And then this independence of coordinates, he also asserts in these harmonic coordinates. Okay, so plus harmonic coordinates. Okay, this is a very important paper in our field. Questions? No. Okay. So then you can ask, now I explained it for EADM, what's the matter with PADM? So with the linear momentum, and there it's actually much easier. I'm going to call it a remark. PADM again is a surface integral at infinity. And it's over Kij minus trace Gk Gij xi over a. Yeah, I'm just copying it here. It's the same expression as above. And then if you perform the same idea as I just showed you in the Newtonian case and that Bartnik used in the case of the energy, if you perform a divergence theorem now backwards, you get a volume integral over the divergence of this Ki, j Kij minus trace Gk Gij plus lower order terms plus an inner boundary term. So then the convergence of the P, it's really Pj, depends on this convergence of the volume integral for the same philosophy as before, but this is immediately already Gi, drift I, so it's Gj. And this we assume to be integrable, so the volume integral is no problem, and you don't even need to make this lower order term argument, and the inner boundary term is also finite, and then the dependence on coordinates is also worked out in these Bartnik harmonic coordinates. Okay, so here it's actually simpler because it's exactly already almost in the form of a divergence theorem. Okay.
We got one question here.
Sure.
Harry asks, could you explain the significance of Bartnik's result again?
So the significance of Bartnik's result is that this term that was defined via Hamiltonian systems analysis actually via this and results in these surface integrals at infinity is first of all actually converging to a number for each asymptotically Euclidean coordinate chart with eta bigger than 1/2. And this number is independent of which coordinate chart you used, and you can compute it in any one you like. So it's actually a physical quantity of the initial data and not a quantity of the initial data with the chart you have. Remember this example by Denisov and Soloviev, where on Euclidean space, we were free to just pick some asymptotically Euclidean coordinate chart of some rate eta equals 1/2, and we could produce any energy we liked. Then that energy is clearly a property of the asymptotic chart and not of the physical system, the initial data set. What Bartnik ensures is that if we assume eta bigger than 1/2, then indeed it's a physical quantity of the initial data set and not a quantity only of the coordinates. And in fact, it doesn't depend on the coordinate chart at all. The story for P is a little bit more subtle because, of course, a vector should depend on coordinates, and it does. So if you rotate your coordinates, then the P has to co-rotate somehow. So I can't say it's independent of coordinates. What I can say is in each coordinate size, the 3 numbers in the vector are finite, they converge. And if I use 2 different asymptotic coordinate charts, then I can use the asymptotic difference between these charts to understand how their linear momentum vectors are related. Okay, so if, for example, I rotate my coordinates and then I do some lower order modification as well, then the net effect will be that of a rotation or of a translation if I do that. Okay, so the Bartnik result about the ADM energy really tells you it's a physical thing. It's meaningful. And of course, many of you will know about the positive energy and positive mass theorems that are all theorems about geodesically complete initial data sets with with such decay eta bigger than 1/2, and telling you that some of these quantities are positive, or that the energy momentum vector is time-like or zero, and things like this. All of these things are also indicators that this is a great notion of energy, but many of them would be void if it was coordinate dependent or couldn't be proved. Yeah? Wouldn't be possible to prove, even though actually the Witten and Shen-Yao proofs of the positive energy theorem are older, and positive mass theorem are older than Martnick's result. But they used eta equals 1 in the beginning, okay, where things are easier. And for the person who was interested in the higher dimensional case, the 1/2 is a 3-dimensional threshold, and you will have to use, I think, n-2/2 in higher dimensions, where n is the dimension of the space, the spatial slice. Yeah. Okay. Any further?
I guess this one's for me. So I guess it's also known. I guess it must be. I never thought about it until now. It's also known this is conserved in time as well, is it?
Yes, it's known. It's known under these conditions that it's conserved in time, and that it transforms covariantly under boost. And if you translate your coordinates, then it translates. Then it's also invariant. Sorry, if you rotate it. So all it's Poincare covariant. So the energy momentum vector EABM is Poincare covariant if you're sitting inside some asymptotically Minkowski in spacetime, meaning that lapse and shift decay as they would in Minkowski.
Okay.
This is covariant. Yeah. Great. That was my next comment on my notes. Thanks. Okay. So then let's use the last half an hour for the center of mass, right?
It's only an easy one, right? So it'll be okay.
Yeah, we've got everything that we need, almost. Okay, so you might have been surprised that I even showed you anything Newtonian. I hope it was helpful in understanding this argument for the finiteness and well-definedness and everything of the ADM quantities, but it will become somewhat even more important now, because we will start the center of mass considerations in Newtonian gravity. Okay, and I want to define a new coordinate chart. So if I'm given, as before, M3, T, K, mu, and J, satisfying the constraints, and AE of order eta is 1/2 plus epsilon for some positive epsilon with respect to some chart X. This is what I'm given now. What I'd like to say is that there is a very beautiful notion of center of mass, a nice analogy to these ADM quantities that I can compute with respect to this chart X, and then I know where the center of mass is. Bad news? No. There is a formula, and I'll talk about this, but it doesn't converge in many cases. Okay, and also it doesn't necessarily give you the result you would hope for. And I'll show you some examples in graphs in Schwarzschild later. Okay, so here's a new chart that we're going to consider over and over again, and it's y is sine of ln of x of y a. Sorry, I messed it up. That's to be expected. So I have x is y plus sine n, where a is a non-zero vector in R3. And my new chart is y. So it's implicitly defined. And the reason why I'm only defining it implicitly is because the computations are much simpler if I define it implicitly. I could just, instead of using the logarithm of the absolute value of y, use the logarithm of the absolute value of x, and all the phenomena would be the same, but the computations would be about 10 times as long. Okay, so that's why I'm doing this, implicitly defined. And I might have to excise a slightly larger compact set for this to actually be a coordinate transformation and so on, but nothing serious is going on there. And indeed, the computation shows that the the same initial data set, then will also be asymptotically Euclidean with respect to these coordinates y, and again of order faster than 1/2, even the same order. Same. Okay, so this is a perfectly nice, very strange, but perfectly nice coordinate transformation near infinity that I can perform on my initial data set. That gives me a new chart in which my initial data set is also asymptotically Euclidean of the same rate. Okay, so why would I do that? Well, because this chart shows me what can go wrong. So if I go back into my Newtonian picture, I can show you already in the Newtonian picture why this is messy. Recall I showed you in the Newtonian picture that the total mass can be written as a surface integral near infinity or at infinity via a divergence theorem using the Poisson equation for the Newtonian potential. And now I can do something very similar for the center of mass. So the center of mass in Newtonian gravity, the total center of mass will be defined as 1 over the total mass times the volume integral over the matter density weighted with the position. That's what all of you would write down after, possibly after some thinking, for a definition of total center of mass for a system in Newtonian gravity. So the first thing you observe, if you want to do this, then this should better be integrable, which is a harsher requirement than just rho to be integrable, because x grows linearly in the radius as you go out to infinity. So that's one condition you should expect from this consideration to come up, that ux and jx in relativity should be integrable. So we expect u x I and jixj should be integrable for all I and j. Yeah, that's by analogy, we should expect that. And now this is the center of mass with respect to this coordinate chart x. Of course, in Newtonian gravity, I would never do strange coordinate transformation. I would usually only do Euclidean motions to my Cartesian coordinates and only consider Euclidean notions. But if I want to illustrate now what happens in GR already happens in Newtonian gravity if you allow yourself to use asymptotically Euclidean coordinates on Euclidean space. So use the y from above. So let's give this some kind of star. Use y from star and compute cy for the Newtonian potential of a point particle. Okay, so now I'm not focusing on the matter density, but I'm saying, okay, let's just look at the simplest Newtonian potential that's non-trivial that I know. And this is R being the absolute value of x. So this is the potential I'm looking at on Euclidean space. And now I'm looking at this in these funny coordinates. And I can actually rewrite this via a divergence theorem, or actually rather a Green's formula as a surface integral. And I won't have the time to do that. So using a Green's formula, can rewrite this as a surface integral at infinity. Just as we did for the mass before, we can do that also for the center of mass. We plug in the Poisson equation and then use the Green's formula and write it as a surface integral at infinity, depending on derivatives of u, partial u, partial xi, okay? And of course on x, j also, yeah? And then if you do that for this specific example already, for the specific example of the point particle Newtonian potential, and we compute the center of mass with respect to these new coordinates y, recall the Euclidean metric is perfectly fine asymptotically Euclidean of rate faster than 1/2 in these coordinates, so that's not the issue, then this will diverge. So this is interpreted as a limit of integrals over spheres near infinity, this will diverge. Okay. where we should expect it to be in the origin, really, because this is the point particle sitting at the origin, and the Newtonian potential it generates, so the center of mass better be in the origin, and it is. If you look at the Cx, of course, that's in the origin, but in this new coordinate chart that is shown at the top of the slide, this new coordinate chart, because of this sign of the logarithm, it oscillates. What you will find is if you look at a fixed sphere of some fixed radius, large radius r, and you look at the surface integral over that sphere, you will get some contribution in the direction of this vector a. And then if you change your radius, it will oscillate back and forth between a and minus a with a speed that's like sine of the logarithm of the length of the radius, approximately. So it will converge, and while you go out along your spheres, it will oscillate back and forth. So of course, in Newtonian gravity, there's a very clean way to say, well, this is nonsense. This is a nonsensical chart. But in relativity, we don't have preferred charts. We don't have Cartesian coordinates where we can say this is a problem of the chart. So this is where the mess begins, really, yeah? So already, if you don't do GR, but just do Newtonian gravity and introduce one feature of GR, that is coordinate freedom as long as asymptotic Euclideanness is preserved, then the mess is already there. And we can't possibly hope that the mess will go away once we move on to GR. And we will recover that same mess. It can be shown to exist also in spatial Schwarzschild. If in spatial Schwarzschild, in these coordinates x that we looked at previously, you switch into these coordinates y, for the notions of center of mass that I'll show to you, they all have the same effect. Okay, so let me write down the mark, and I can't show this to you in detail today. The same coordinate transformation star causes the same issue in spatial Schwarzschild. And this is regardless of which definition of center of mass you use. And let's be careful and say among the ones I'm presenting, but I'm pretty sure that any reasonable definition of center of mass will do the same in presenting. So we can't get around this. We also learned, let me highlight this again, that we should expect that these things should be integrable in the end by this analogy. Okay. So whatever the definition of center of mass is, we should, let me just test this because this is nasty, we should expect that if it converges in one chart X, and then we construct a new chart Y, a new asymptotic chart Y, then it diverges. And if it diverges, we don't know if it's just in a bad coordinate chart or if it's a system with non-converging center of mass. Any questions at this point?
We got a couple of ADM ones, but I'm going to leave them till the end, so not to interrupt your flow. Yeah.
Okay. Perfect. So then let's say, what definitions of center of mass are there? So what is center of mass? And there's several approaches. And today I want to focus on two approaches. One is the Hamiltonian systems approach. Similar to the ADM one that I talked about before. And one is via foliations. And then the others, for example, by Chen, Wang, and Yao. But I'm not going to talk about that here. And we expect that they give the same result as the final foliation definition that I'll show you today. So let me say very briefly about the Hamiltonian systems approach. This was done by Baig and Omehu. Building on work by Reggie and Teitelbaum. Looking if I can find, no, I deviated from my notes too much to find the years, sorry. So what they did is they used the same Hamiltonian systems approach that Arnold, Dieser, and Misner used to derive a surface integral at infinity formula for the center of mass. And this is called the Omohu, Reggie, Teitelbaum center of mass. Reggie and Teitelbaum did this first, I believe, in the 70s. And then there was a small gap or error that was closed by Beck and Omohu, I think, in the 80s, but I may be off with the decades. And the formula is similar. And the important thing I want to point out is that this is a surface integral at infinity, over Gij k and Gij L. So before we saw the mass, the energy was a surface integral over first partial derivatives. Now the center of mass is an integral over first and second partial derivatives of the metric, and in particular, not k. So the second fundamental form doesn't go in there. And of course, it doesn't always converge, and there's some sufficient condition for convergence written down by Reggie and Teitelbaum, and we can talk about those later if someone is interested. But for now, let me say that it doesn't always converge under these asymptotic Euclideanist conditions that I mentioned, as we should have expected from the example already in Newtonian gravity, and it doesn't involve k. Doesn't always converge. Okay, so this for this, and now let's move to the foliations. And the idea in the foliations goes back to Mr. Dulu and Yao, who suggested to do this, and then Husken and Yao, who actually did it. And this, I remember the year, this is 96, the Husken and Yao paper. And the idea there is as follows. You have your manifold here, your initial data set, and they really forget about the k also in their approach. So maybe let me write it like this. And then you have your asymptotic chart here, as I drew it before, outside some compact set, into the exterior region of outside some ball. And then what they do, Husken and Yao do, is they construct a foliation by two surfaces that are large and almost round, and then have the property that they have constant mean curvature. Yesterday I mentioned that mean curvature is going to be important again. So now this is the mean curvature H I was talking about, the mean curvature of the two surfaces within the 3 space. No space-time reference here at all. So codimension 1 mean curvature, and then they map these surfaces, and I should probably draw this one in a different color to make this more clear. Yeah. They take them and map them to Euclidean space, where they then can say how round they are and everything with respect to the Euclidean metric. And foliating means that every point outside some maybe larger compact set sits on precisely one of the surfaces, and all the surfaces, and this is somehow smooth and non-degenerate. All the surfaces have the same dimension, and they're actually all 2 spheres. And then you can map them over here. And then in Euclidean space, for each of these surfaces, and I'm going to call them sigma h for a constant mean curvature h, if you compute the average position of the point on one of these surfaces, then you can think of this as a point in Euclidean space, and you can perform the average of, you can perform the limit as you go out along the foliation of this average point, of this average position of a point on the surface. So in this, if I remove for now this interior, so we can see it better, I will have for the blue surface, this will be some point here, and for the green surface, this will be some point in Euclidean space there. And if, because I have a 1 parameter foliation, I will have a 1 parameter family of average positions of these surfaces in Euclidean space. And they said that the center of mass, CMC center of mass, with respect to this chart, should be defined as the limit going out along the foliation, meaning that the mean curvature goes to 0 of these average positions. And I should really put this here, X. Okay. The problem is And this is a result of mine with nets in the paper that I referred to yesterday, which I believe is from 15 or 16, that this doesn't always converge. And I'm being very sloppy here. So Husken and Yao did this under very strong decay assumptions, and subsequently many people, including Metzger and Huang and Christopher Netz and many others, analyzed this under weaker and weaker decay assumptions. And now we know that this foliation by constant mean curvature spheres exists under the optimal decay assumptions, where eta is 1/2 plus epsilon for any epsilon. Whenever the ADM energy vanishes, then you have this foliation, and it's unique in a certain sense, in a certain a priori class. But then Nertz and I found that it doesn't always converge, even in this very strong original decay scenario that Husken and Yao considered. And the example is a graph in Schwarzschild. As we discussed, where the graph function is the sine of the logarithm, and this should look familiar to this other example of x plus a dot x over r for some non-trivial a in R3. So this is the graph function. It's very flat. Recall that we said that whenever t is bounded or decays, then certainly we have asymptotically Euclideanness of the graphical initial data set. This is an asymptotically Euclidean initial data set. It's even asymptotic to Schwarzschild. It doesn't even disturb Schwarzschild at this 1/r order. It only comes as a change from Schwarzschild in the r-2 order. And still, the center of mass doesn't converge, and it does the same thing. It oscillates between a and minus a indefinitely, more slowly and more slowly, but it never stops. This effect we can remedy in a paper with Anna Sakovic, which was only published last year, but the result has been around for a while. So if instead of looking at constant mean curvature surfaces, as Husken and Yao and subsequent works do, we look at constant space-time mean curvature surfaces, as I explained yesterday, then we also get a unique foliation of a neighborhood of infinity of our initial data set with non-vanishing energy. So we get a unique foliation by surfaces of constant space-time mean curvature. And we call those ST-CMC for space-time constant mean curvature, where these are called CMC for constant mean curvature in the literature. And along this foliation, of course, it would be nice to use a definition like this, also to define a center of mass. And we do so, but we know already that they won't always converge, because if they converge in one chart, and then you do this star coordinate change that I showed you earlier, that also messed things up in Newtonian gravity, it will mess things up here. Okay, so ST-CMC does not always converge. But, and here's the big but. So first of all, it does involve K, because it's space-time constant mean curvature. So it does involve K. And it transforms, if it converges, it transforms equivariantly under the Poincare group. In particular, the center of mass now evolves like a point, like the position of a point particle in special relativity under Einstein evolution. So we have EDT of C is P over E, and this is the ADM stuff, and this is ST-CMC in particular. And this is in some sense even true if it doesn't converge at some infinitesimal level. The rate of change on each finite surface before you take the limit, the rate of change is asymptotically this. And we get a correction term for this Reggie Teitelbaum center of mass from Hamiltonian mechanics, Hamiltonian systems analysis, involving K. Okay, so what I'm saying is that using this foliation idea, but using a different concrete foliation, namely foliation by constant space-time mean curvature, which takes the K into account, what we get is something that is covariant under Bus and evolves like the position of a point particle in special relativity under Einstein evolution, and has small corrections to this Begomov-Reggie-Teitelbaum Hamiltonian systems analysis approach. And furthermore, in this example, in this graphical example in Schwarzschild, it's fixed. Where I said it diverges in this funny graph, it's fixed. And here, what we do get is that this center of mass in the same chart that they considered, that we consider to find a counterexample to this CMC center of mass, this is actually 0, as you would expect in Schwarzschild. Okay, so for all the graphical cases, it's very, in Schwarzschild, it's very clear that this is the right notion of center of mass. And I promised to end with some open problems. So let me use the remaining few minutes to remark on the open problems. So, of course, you can ask similar questions for initial data sets with different asymptotics. And I should warn you that some of this is being done currently by a student of my collaborator, Anna Sakovic, but not all of it. So there's still some work to do there. And then another question that I think is maybe more suitable for the mostly physics community I'm talking to here is, I want to understand what's going wrong in the Hamiltonian systems approach. Why is it giving me a center of mass that doesn't involve K? Why doesn't it give me this correction term? And is there a way of somehow refining this Hamiltonian systems analysis? And it involves K in a quadratic order. So it really involves K times K in some sense, yeah? So maybe I need to do a more refined Hamiltonian systems analysis to get this quadratic in K term also from Hamiltonian systems analysis. And one refined Hamiltonian analysis to produce this K times K correction term. Or in other words, what's wrong now? What's wrong with it now? And I'm not trying to imply that someone made a mistake in applying the method. I'm really thinking that maybe there's something fishy going on when this method, which is very classically mechanically, is applied to the scenario of GR. Yeah, I'm not saying anyone made a mistake here. And then one problem that we're working on that I just wanted to mention is, I told you that in some charts things converge, and then you can construct this funny chart in which they always then have to diverge. Is there an a priori criterion of what is a good chart? Yeah, what is a good chart? And of course, in Newtonian gravity, a good chart is a Cartesian chart, or anything that decays to a Cartesian chart suitably fast. And in relativity, we don't have that, except when we have symmetry, maybe. But typically we don't have symmetry. And then what is a good chart? Is there some nice condition? And I mentioned in passing that Bartnik introduces this harmonic coordinate chart to deal with energy and linear momentum. And of course we checked that, and it's not good here. Not good enough, not quite good enough. It's very subtle, but it's not quite good enough. So Bartnik's harmonic coordinates. And not quite good enough. And this is joint work with my postdoc Melanie Graf and with Jan Metzger from Potsdam, which is still ongoing. And the reason why it's not good enough is because the harmonicity condition, again, doesn't involve K. And somehow it seems that if you don't know about K, you don't know enough. recalling that k is the infinitesimal velocity or momentum of the thing, the center of mass should know about its relative velocity to the observer, its relative momentum. So thanks at this point, and I'm curious to hear all the questions.
Okay, thank you. So we got a couple of questions, maybe people have other questions, but we've got a couple built up from the ADM stuff, and then he's going to ask type in center of mass questions maybe while you're answering these. So the first one was from Gopal Yadav again. And so this was he asked the earlier question about the higher dimensional ADM. And so his second question was, for example, if the space-time is R13, I guess Minkowski, R13 times R times M6, which is a compact 6-dimensional manifold, then how would one treat the Minkowskian R13 space-time?
Okay, so here we're reaching the border of what I'm familiar with. The point is that I think that the manifold you're mentioning with this wouldn't be asymptotically Euclidean, because you can't just excise a compact set and then be diffeomorphic to R of the correct dimension minus a ball, right? So I think, going back to the picture, I think you already don't have this charge. Not even speaking about the decay in that chart of certain quantities, because if you have a compact factor, this won't give you a direction at infinity in this chart. So I would think that the whole approach doesn't work there. But I may be off. Maybe someone has figured out a way of doing that I'm just not familiar with.
Okay, and our second question was from Vikar Hussain, and it's also on ADM. Is it conceivable to have a coordinate-independent derivation of the ADM quantities?
Is that coordinate dependent or independent?
A coordinate-independent, yeah.
So I don't know of any derivation, but there are certainly expressions you can write down, limits over Hawking masses or limits over other kind of quasi-local masses, which limit to the ADM energy or ADM mass in under some decay assumptions, maybe even those weak ones I discussed here. And then if those are invariant, like Hawking mass, for example, then that's an invariant limit way of defining the ADM energy. But as far as I know, historically speaking, they all came after the fact that ADM derived these quantities. And I wouldn't know of a coordinate independent way of deriving these very quantities other than saying, okay, later we found that there is some way of approximating them by coordinate independent quantities.
Yeah, I know from my PhD from many years ago now, the Brown-York mass limit. I mean, I guess all quasi-local masses, that's like one of the things you do when you define it. You have to limit ADM, right? So it's kind of self-fulfilling in a way, I guess.
Yeah, in some sense.
Okay, so you were talking about the good charts. And so I don't really have, I had a bit of a, well, maybe a comment on this. I know, like, when I go to some numerical relativity talks, and people often do stuff in numerical relativity where, you know, you just define a center of mass or an energy and a center of mass in a particular way, you know, almost a coordinate dependent thing. And then often they get, and there's no real reason to expect it to work, but often they get things that sort of seem okay, right? And sometimes there's discussions about, like, you know, we just did something crazy, like, why should this have worked? And so, and then sometimes people will say, well, you know, I guess the coordinate systems that they use in numerical relativity, when they pick their latch and the shift, you're effectively picking certain coordinate systems. And often these coordinate systems seem to generate better behaviors than you might expect, right? Things like gravitational wave fluxes versus things at infinity, they often seem to match up in unexpected ways. So I don't know, and I guess they're often harmonic or related to harmonic, right? So maybe there's some clue just from what people have done there on.
Thanks for the comment. So maybe I should clarify this. What I'm using as harmonic is harmonic with respect to the spatial metric. So this is the Laplacian of the coordinate function 0. The harmonic that I believe you're referring to, it would be space-time harmonic. So the D'Alembert of them would vanish, which means you can keep them freely initially, and then you evolve them by the D'Alembert along with the Einstein flow, right? Am I understanding this
I
correctly?
think so. Yeah, I'm a bit hazy actually, but I think it might be something like that.
Okay, so then that notion of harmonic, which I would call wave harmonic to distinguish them now, because it's a wave equation and not a elliptic equation, that knows about the space-time evolution.
Yeah.
Right, at some level.
Yeah.
While
Yeah.
the harmonic coordinates that Bartnik picks, they're completely tied to the Riemannian metric only, and the only reference they have to K to the second fundamental form of the initial data set is through the constraint equations.
Right. Okay.
Right. So I'm completely happy to believe that if I choose nice coordinates initially, because I'm gluing two curves together in some way, or I have initial data construction methods that come with somewhat nice coordinates near infinity, and then I'm involving the coordinates via the wave harmonic procedure, then I will stay in that nice class. So that would be like, if we have a nice class, then that would be a good test to see how nicely the class evolves, yeah,
right.
under, for example, wave harmonic gauge. But that doesn't help me on the initial level of the initial
right.
data, because for wave harmonic equations, I can prescribe any initial data.
Right, sure.
So it doesn't give me, as far as I understand, a constraint on this type of coordinates I want to use initially.
Yeah, no, I think that's right. Yeah, yeah.
And I could also try, I mean, I showed you this example of Denisov and Soloviev, where they showed that you need eta bigger than 1/2, and otherwise the ADM energy is not well defined. Then you could, of course, try a similar trick and just say, okay, let eta be bigger than 1, and then maybe the center of mass is well defined. But if you do that, then your energy becomes 0, and then center of mass ends up being well defined anyway, because then you're empty in some sense, right? So that's not a good trick. So then what Reggie and Teitelbaum suggested are some type of parity conditions. And if you pose these parity conditions, then these integral will converge. But then what we prove with Melanie Graf and Jan Metzger is that there are many initial data sets that don't have any coordinates that satisfy these parity conditions. And moreover, the parity conditions don't transform nicely under coordinate translations. So if you have them in one coordinate chart and then you translate the chart, then you break them potentially. And there are examples where you really break them. So it's not a Poincare covariant set of coordinates, or not a Poincare covariant set of conditions, right? So there are many approaches, and all of them have their offshoots, and they can be used in numerical relativity or also in proving theorems. But I don't know of any geometric one for the precise question we have here.
Okay, I'm not seeing other questions. Maybe I'll just ask one other thing. And so I guess the other thing, I mean, if you have a center of mass and you have a momentum, then I guess you'd really like to have something which said your center of mass was moving with that momentum, right? But I guess that would be even harder, because then you almost need a background, your space to be background Cartesian or something, right, for that to work.
You want something like this?
There. Yeah, maybe I lost track there. Yeah, okay.
Yeah, so what's going on there, and it's easy to lose track of it. So what we have is we have an initial data set which has this STCMC foliation near infinity, this space-time constant mass, constant curvature foliation near infinity in the manifold. So that's without any reference to any chart, right? And now you forget the right half of what I drew, and you stop here and only consider this part. And now this initial, and you think of the whole initial data set, which has this, or the exterior region of some compact set, which has this foliation. And now if you evolve this in your Einstein flow to generate a space-time, or within a given space-time with lapsing shift asymptotic to a time translation in Minkowski, then what you can do is you can track each individual leaf of the foliation in time. Okay, and what happens is that it will deform a little bit and it will translate a little bit. And what we can show is that this translation in time of an individual one of our leaves of a fixed curly h, so that's sort of a measure of its size. And if we track an individual one, then it sort of runs through something which is almost a skewed cylinder. And the slope, the dominant part of the slope is P over E. So even if nothing converges and without reference to any coordinates specifically, I mean, we need coordinates to have P, but that's it, yeah? Then we can show that the cylinder is tilted in the direction P over E, plus lower order terms. And then if the limit, the center of mass limit in my given chart converges, then it will converge also in the future. And then we will have this time evolution law.
Oh, right, okay.
So that we have, and we have something similar, which isn't finally written out. This is with Hanna Sakovic, and we're also currently working on proving something similarly subtle for the boosts, yeah? And I mean, there's no reason to expect that it shouldn't work. And we have it, it's just tedious.
Right.
So if you look at a large candidate from your foliation, everything works really nicely, even without the center of mass converging.
Neat.
Yeah.
Okay, so, I'm not seeing any other questions. So maybe we thank Dr. Cederbaum again. I'm the only one who can clap, so I'll do it. And we have our next session in 50 minutes. So thanks again.
Sure, and I'll be happy to send the slides again.
Yeah, oh yes, that's right, thank you. I always forget these things. Yes, if you can send them, and then we'll post them, yeah.
Cool. Okay.
And lots of thanks coming in now on the Slack. You can have a look at them afterwards if you want. Okay. Thank you.
Thanks. Bye.